You are doing it right now. You've probably done it, I don't know, maybe 12 times in the last minute alone without even giving it a single conscious thought.
Yeah, exactly. It's just automatic.
Right. We're talking about breathing, sucking in air. I mean, it feels like the absolute simplest thing in the world, doesn't it? You just expand your chest, air rushes in, you let it go, air rushes out.
It really does feel that way.
But, when you actually look under the hood, breathing is this incredibly bizarre, explosive, highly engineered mechanical and chemical symphony.
Oh, it truly is a symphony. And, well, to really appreciate it, we need to follow the actual journey. In this deep dive, we're taking a single breath of air from the atmosphere, pulling it through all the anatomical pipes, and tracking it all the way down into the microscopic air sacs in the lungs.
Right down to the tiny details.
Exactly. Our mission today is to completely shatter the illusion that breathing is just, a simple bellows system. We've pulled together an incredibly in-depth medical deep dive on pulmonary ventilation. And honestly, if you look at the anatomical blueprints and airflow charts I've got pulled up on the screens behind me here, it looks way more like the schematics for a jet engine than a human chest.
I love those charts, mostly because they show just how much is happening every single second. But to understand that journey, I mean, we really have to start with the physical machine that pulls that air inside you.
Right, the mechanics of it.
Because here's the first thing that completely threw me when I was looking through our research. The lungs themselves, they actually don't have muscles.
They don't.
They can't pull themselves open. So if they are totally passive, how on earth are they expanding?
That is the perfect place to start. The lungs are essentially just passive elastic structures. I mean, if you took a lung out of the body, it would just collapse like a deflated balloon.
Just completely flat.
Exactly. To get air into them, the body relies entirely on the box they are sitting inside, which is your thoracic cavity. And the body uses two main methods to change the size of that box.
Okay.
The first one, which is the main driver for your normal, quiet, sitting on the couch breathing, is the diaphragm.
Okay, let's unpack this. The diaphragm sits at the bottom of the chest cavity, right? Kind of like a dome.
Yeah, exactly like a dome. And when it contracts, it pulls downward. It physically lengthens the chest cavity, and it drags the bottom of the lungs down right along with it.
Oh, so it's essentially acting like a syringe.
That's a great way to picture it. When you pull the plunger down, you create a vacuum, and air rushes in.
But that's just for resting breathing, right? What happens when I'm, running or carrying something heavy? The plunger just isn't enough then.
Correct. That's when the second method kicks in, which is elevating the rib cage. And actually, I want you to try this right now. If you were listening to this, sit up straight and take a massive deep breath.
Okay, doing it now.
Feel your ribs. In their resting position, your ribs actually slant downward towards your waist. But when the muscles of inspiration, specifically your external intercostals, when they contract, they pull the ribs up and forward.
Oh, wow. Yeah, the whole sternum moves away from the spine.
Precisely. It pushes your chest outward, and that increases the front-to-back thickness of your chest cavity by about 100%.
That's a huge difference.
It really is. So you have a downward pull from the diaphragm and an outward pull from the ribs.
But hold on, let me see if I have this right. The ribs are pulling out and the diaphragm is pulling down. But you just said the lungs are totally passive, deflated balloons.
Right.
And our sources point out that the lungs aren't actually attached to the chest wall. Aside from right in the middle where the blood vessels enter, they are literally just floating in there.
Yes, just floating.
So if they aren't glued to the ribs, why do they expand when the ribs move? Why doesn't the chest just expand around them?
What's fascinating here is that you've hit on one of the most elegant pieces of engineering in the human body. They aren't glued, no. They float in the thoracic cavity, completely surrounded by a microscopic layer of fluid called pleural fluid.
Okay, so are the lungs and the chest wall essentially like two wet pieces of glass stuck together?
How do you mean?
You know how you can slide two wet panes of glass around freely against each other, but if you try to pull them straight apart, that suction just holds them incredibly tight.
Yes. The wet glass is a great starting point, but the reality is actually even more active than that. That suction you're describing is called pleural pressure.
Pleural pressure, got it.
Right. But it doesn't just exist passively. Your lymphatic system is constantly draining excess fluid from that tiny space between the lungs and the chest wall.
Oh, like a pump.
Think of it as a microscopic sump pump that never ever stops running. That continual drainage creates a permanent, slight negative pressure. It's a vacuum, usually about -5 centimeters of water, dropping to about -7.5 when you inhale.
So the body is actively sucking the lungs against the inside of the ribs?
Exactly. At rest, it's a mild suction.
Wow.
But as your chest expands during a breath, it pulls outward, and that vacuum becomes even stronger.
That's amazing.
Yeah, and that perfectly lubricated constant suction is what forces the lungs to expand right along with the rib cage without tearing or detaching.
And because the lungs get stretched open, the pressure inside the little air sacs drops below the atmospheric pressure outside your face.
Exactly. Alveolar pressure drops.
Right, and nature hates a vacuum, so air gets sucked into your nose to balance the pressure. Then you relax, the chest shrinks, the pressure inside goes up, and the air is pushed back out. I mean, it's brilliant plumbing.
It is.
But wait, once we get that air down into the lungs, we run into a massive physics problem. Our sources call it the surface tension problem, but, I keep thinking of it as the wet balloon problem.
The wet balloon problem is a very apt name for it. And this is where the engineering of the lung moves from brilliant plumbing to miraculous chemistry.
So, inside the lungs, there are millions of these tiny air sacs, the alveoli. This is where the actual swapping of oxygen and carbon dioxide happens.
Right, the gas exchange.
But to do that, they have to be coated in a thin layer of fluid, right? Which brings up a question, why are our lungs wet in the first place? Why didn't we just evolve dry lungs to suck in dry air?
Well, if we connect this to the bigger picture, the moisture is an absolute non-negotiable requirement for biology. Oxygen cannot simply cross a dry biological membrane into your blood.
Oh, really?
No, it physically has to dissolve into a fluid first before it can pass through the cell walls. So the lungs absolutely must be wet.
That's right, but water is incredibly sticky. Like, water molecules are highly attracted to each other.
They are. Think of a raindrop falling through the sky. It doesn't just spread out into a mist,
And
right?
it stays together.
It pulls itself into a tight, hard little sphere because the water molecules on the surface are constantly attempting to contract, to pull closer to one another.
Okay, I'm with you.
Now, take that raindrop and reverse it. Apply that principle to the inside of a tiny spherical wet balloon in your lung.
Oh, I see. That water layer lining the inside of the air sac is constantly trying to contract into a raindrop, which creates this massive force trying to crush the lung from the inside.
Actually, the physics are even more brutal than that because of an inverse relationship. The smaller the bubble, the harder it is to keep open.
Wait, really? The smaller it is, the harder it is.
Yes. If your alveoli were lined with pure water, the microscopic tension would be so strong it'd be like trying to inflate a heavy, stiff car tire with just your lungs.
That sounds impossible.
It practically is. Your respiratory muscles would become completely exhausted after just a few breaths. The collapsing pressure would be immense. You simply wouldn't have the physical strength to pull those tiny wet balloons back open once they snap shut. Pure water has a surface tension of about 50 dynes per centimeter, which is just too high.
Here's where it gets really interesting to me. If water's surface tension is actively trying to collapse our lungs and kill us, the body must have a workaround.
It does.
Our research mentions this thing called surfactant. Is surfactant basically acting like a biological dish soap to break that tension?
It's significantly more sophisticated than your kitchen soap, but it operates on the exact same chemical principle.
Okay, cool.
Surfactant is a complex mixture of phospholipids, proteins, and ions. It's manufactured and secreted by specialized cells deep in the lung walls. You can think of them as tiny biological factories.
Type 2 alveolar epithelial cells, right?
Exactly, good catch. When this surfactant mixes with the water in the alveoli, it doesn't just dissolve evenly.
What does it do?
Part of the molecule dissolves into the water, but the rest of it stays on the surface, physically getting in the way. It wedges itself between the water molecules, disrupting their attraction to each other.
Like breaking up a crowd.
Exactly. It takes that massive collapsing force, that surface tension, and drops it from 50 all the way down to between 5 and 30. It drops it by up to 90%. It is literally the only reason your lungs don't crush themselves every time you exhale.
And this isn't just some abstract physics trivia either. This has massive real-world medical implications, right? When we look at premature babies, this is exactly the battle they're fighting.
It is exactly the battle. This mechanism is why premature birth can be so incredibly dangerous for the respiratory system. Fetuses don't actually begin secreting surfactant into their lungs until between the 6th and 7th months of gestation, sometimes even later.
And if they're born before that biological factory turns on, they just have pure, sticky water in their lungs.
Yes. And remember that inverse rule we discussed.
The smaller the bubble, the higher the pressure.
Right. A premature infant's air sacs have a radius less than a quarter of an adult's.
Oh, wow. So they are incredibly tiny, meaning the collapsing pressure is just off the charts.
Precisely. Without surfactant, their tiny alveoli have up to 8 times the normal tendency to collapse compared to an adult.
8 times.
Yeah. Every time the infant exhales, the tiny wet balloons snap shut, and it takes an immense, exhausting amount of pressure to force them open again. It leads to what we call respiratory distress syndrome.
That sounds terrifying.
It is. Thankfully, modern medicine can step in with continuous positive pressure breathing and artificial surfactant therapy, but it shows you just how razor-thin the margin of survival is without that chemical intervention.
It really puts into perspective how finely tuned this system is. I mean, we have the diaphragm acting as a plunger pulling the lungs open. We have the biological dish soap keeping them from snapping shut.
All working together perfectly.
So what does this all mean for the actual air we are moving through this system? Because reading through the data on lung capacities, I was honestly stunned by the sheer volume of air we process.
The volumes are staggering when you really measure them. We use a process called spirometry to track this, and it reveals just how dynamic human lung capacity really is.
Right. So a normal, quiet breath, like just sitting here listening, is about 500 milliliters of air. Half a liter.
Which is your tidal volume.
Yeah, tidal volume. That doesn't seem like much. But if you take the deepest breath you possibly can, filling your chest to the absolute brim, the total lung capacity in a healthy young man is around 5,800 milliliters.
Nearly 6 liters of air.
That's insane.
And it gets even more impressive when we look at the minute respiratory volume.
That's the amount of air moved in a minute.
Exactly. The total amount of new air moved into your passages over 60 seconds. Normally, it's about 6 liters per minute. But during heavy, intense exercise, when your breathing rate speeds up and you're taking those massive, deep breaths,
Yeah.
that minute volume can jump to over 200 liters per minute.
200 liters of air a minute. That is wild. Imagine 100 large 2-liter soda bottles completely emptied and refilled every 60 seconds.
It's a massive amount of work.
But here's the catch that I didn't understand at first. Not all of that air is actually doing anything useful for you. We ran into this concept of dead space, which sounds like a sci-fi horror movie, but it's actually just, well, it's the plumbing.
It is the plumbing. And it's a very vital concept. Of that 500 milliliter normal breath you take, about 150 milliliters never even reaches the gas exchange areas.
It just sits there.
It just sits there, filling up your nose, your pharynx, and your windpipe.
Wait, so 150 milliliters just gets stuck in the pipes? That seems like a massive design flaw. Why even breathe it in if it doesn't reach the blood?
Well, because you can't teleport air directly into the deep lungs. It has to travel through thick-walled anatomical pipes to get there, and no oxygen can pass through the thick cartilage of your trachea.
Oh, right, the walls are too thick.
Exactly. So that 150 milliliters of air is entirely useless for oxygenating your blood. It's just taking up space. And when you exhale, that dead space air is the very first thing to leave.
Okay, I think I get it. Is dead space essentially like the water left sitting in a garden hose after you turn off the spigot?
Oh, that's good.
You pay for the water, it went into the system, but it never actually reached the end of the hose to water the plants.
I love that analogy. Yes, the water is in the hose, but the plants are still thirsty. And to take that analogy a bit further, it explains why the most important metric in respiratory physiology isn't how much air you breathe, but your alveolar ventilation.
Alveolar ventilation.
Right. It's not about how much water goes into the hose. It's about the volume of new air that actually reaches the plants, the alveoli, because that is the only metric that actually keeps you alive.
And there's a difference between the physical pipes, the anatomical dead space, and another type of dead space our sources mention, right? Physiological dead space.
Yes, this is a crucial distinction. Anatomical dead space is just the physical reality of the garden hose. But physiological dead space occurs when the plants themselves, the actual alveoli, fail to function.
How does an alveolus fail? Does it, just pop?
Usually it's a blood flow issue. If the blood capillaries flowing past a specific alveolus are blocked or damaged, it doesn't really matter how much fresh oxygen reaches that air sac.
Because the oxygen has nowhere to go.
Exactly. The sac is full of fresh air, but it's functionally dead space. Yeah. In a perfectly healthy person, anatomical and physiological dead space are basically the same.
Okay.
But in certain lung diseases, the physiological dead space can swell to 1 or 2 liters. The person is breathing heavily, but it's like watering concrete. The oxygen just isn't entering the blood.
Man, okay, so we've got to get the air past the dead space and into the functioning alveoli. But thinking about this, these alveoli are incredibly delicate, wet membranes.
Highly delicate.
And we have this massive surface area of them directly exposed to whatever is floating in the atmosphere. You are taking the outside world and putting it directly inside your most vulnerable tissues. That seems incredibly dangerous.
It is an extreme vulnerability.
Yeah.
And it's exactly why the respiratory passageways aren't just empty pipes. They are an elaborate biological air conditioning and filtration system.
And it starts right at the front door, right? The nose.
Yes, the nasal cavity.
As air passes through your nasal cavity, it hits these things called conchae. They look like weird obstructing veins or like speed bumps.
Speed bumps is a good way to describe them.
And they do three things. They warm the air to within 1 degree of your body temperature, they humidify it, and they filter it through a process called turbulent precipitation.
Turbulent precipitation is a brilliant mechanical filter. When the air hits those speed bumps, the conchae, it's forced to suddenly change direction.
Right?
The air itself, being a gas, can easily bend around the obstructions.
Mm-hmm.
But the particles suspended in the air, the dust, the pollen, the ash, they have too much mass and momentum.
They're like microscopic crash test dummies in a car without brakes.
Precisely. They can't make the turn. They crash straight into the mucus-coated walls of your nose and get permanently trapped.
That's awesome.
It's so effective that almost no particles larger than 6 micrometers in diameter ever make it past your nose.
But the system has a major blind spot, doesn't it? Cigarette smoke.
Ah, yes.
The research points out that cigarette smoke particles are tiny, about 0.3 micrometers, so they don't crash into the walls.
No, they don't.
They just ride the air current, smoothly taking the corners, completely bypassing the upper filters, and go straight down into those delicate wet balloons.
Yes. And if we connect this to the bigger picture, it explains the unique devastation of smoking. Up to a third of those tiny particles remain suspended and are eventually exhaled, but a vast amount simply settle and become trapped in those delicate lower regions.
Where they shouldn't be.
Exactly.
Yeah.
And because those areas aren't designed to filter heavy particulates, it eventually causes fibrosis, inflammation, and permanent debility.
But for the normal dust and gunk that does get trapped in the mucus along the way, the body has a cleanup crew, right? The cilia escalator. I read this and I was just stunned. The entire surface of your respiratory passages is lined with microscopic hairs, about 200 of them on every single cell.
And they are never, ever resting. They beat continually at a staggering rate of 10 to 20 times per second.
20 times a second, that's just a blur.
It is a microscopic blur, and their power stroke is strictly directional. In the lower lungs, they beat upward. In the nose, they beat downward.
So they all push toward the same exit.
Yes.
Oh.
It creates a slow, continuous river of mucus, moving a few millimeters a minute, carrying all that trapped dirt towards your pharynx, where it can be harmlessly swallowed or coughed out.
Oh, speaking of coughing, we have to talk about the cough reflex because the sheer physics of a cough are mind-blowing.
They really are.
When a piece of stubborn dust hits the wrong spot in your windpipe, a nerve fires a signal to your brain, and your body initiates this automatic, violent sequence of events. First, you gasp. You suck in up to 2.5 liters of air.
A massive breath.
Yeah. Then your epiglottis and vocal cords slam shut, tightly trapping all that air in the lungs.
And this is where the pressure builds, and it's an incredibly intense muscular event.
Yeah.
Your abdominal muscles contract forcefully, essentially shoving your stomach organs up against your diaphragm, while other muscles squeeze the chest inward.
So the air is just trapped in a shrinking box.
Exactly. The air has nowhere to go. The pressure inside your trapped lungs skyrockets to 100 millimeters of mercury or more.
Which is an insane amount of pressure inside a soft, fleshy chest. And then the vocal cords suddenly rip open. The air under all that pressure explodes outward.
And the velocity is incredible.
Our research notes that because the lungs are compressed so hard, the softer parts of the trachea actually cave inward, creating these narrow slits. So this high-pressure air is forced through tiny gaps, and it blasts out at velocities ranging from 75 to 100 miles per hour.
It's quite literally hurricane force winds inside your chest.
Wait, 100 miles per hour? So when a piece of dust hits the wrong spot, our windpipe temporarily turns into a biological shotgun.
That is an incredibly accurate way to describe it. A biological shotgun designed to physically blast foreign matter out of the sensitive lower airways.
That makes so much sense.
The sheer velocity is necessary because it has to rip the irritant and the sticky mucus it's trapped in off the airway wall and carry it, against gravity, entirely out of the body.
It is just so violent and yet perfectly calibrated to save our lives. But this actually brings us to the final piece of the puzzle, because evolution is incredibly thrifty.
It certainly is.
We've established how this respiratory system acts as a plunger bellows, a chemical lab with the dish soap surfactant, and a high-speed shotgun defense mechanism. But somewhere along the line, evolution found one more spectacular use for all this moving air.
Well, this raises an important question, doesn't it? If you have a system constantly moving highly controlled volumes of air through narrow pipes, what else can you do with it?
It's like evolution looked at this incredibly elaborate gas exchange machine and said, hey, as long as we're moving all this air around, let's use it to make noise and invent podcasts.
Exactly. We repurpose the wind for vocalization. Speech uses the exact same respiratory control centers and mechanics that we've been discussing,
So it's a piggyback system.
fundamentally built right on top of the breathing apparatus.
Yeah.
Phonation, which is the actual production of sound, happens in the larynx.
And this is where the vocal cords come in, which, honestly, I always picture it as actual strings like a piano or a guitar, but they are actually just fleshy folds protruding from the walls of the larynx, right?
Right. During normal breathing, those fleshy folds stay wide open, so air can pass quietly. But when you want to speak, specific laryngeal muscles pull those folds tightly together.
And they belong to the air.
Exactly. As the pressurized air from your lungs is forced between them, they vibrate. Speech is fundamentally just highly controlled, continuous exhalation through a biological musical instrument.
And the level of control is insane. It's so much like a guitar. Inside the vocal folds is a strong ligament attached to the thyroid cartilage, which is your Adam's apple, and the arytenoid cartilages. Muscles can physically rotate these cartilages to stretch or loosen the cords.
Yes, and this stretching is what dictates pitch. The pitch of your voice is determined by the degree of stretch on those cords, how tightly they are pressed together, and the mass of their vibrating edges.
So tighter is higher?
Exactly. If the muscles pull them incredibly tight, with sharp edges, you produce high-pitched sounds. If the muscles relax, creating looser, blunted edges, you produce lower bass sounds.
And that vibrating buzz is just the raw sound, right?
This is a source, yes.
The air then travels up into the resonators. Your mouth, your nose, your sinuses would shape that vibration into the unique quality of your voice, which actually completely explains why you sound so weird and nasally when you have a cold. Your nasal resonators are physically blocked by mucus, so the sound waves literally can't bounce around in there.
Precisely. The vocal cords generate the raw acoustic energy, but the resonators give it humanity, vowels, and individual character.
It's just unbelievable when you step back and look at the whole picture. I mean, we've gone from the diaphragm acting as a physical plunger, pulling open a vacuum-sealed cavity, to the life-saving biological dish soap of surfactant, keeping the wet balloons from crushing themselves. We've navigated the garden hose dead space, watched the microscopic crash test dummies in the nose, the 200 beat per second cilia escalator.
Survive the 100-mile-per-hour biological shotgun cough.
Yes, all the way to the finely tuned vibrating cords that allow humans to speak, to sing, to share knowledge. It is a profound reminder that every single breath you take is an absolute physiological miracle.
It is a miracle of adaptation and a true testament to how life finds a way to balance incredibly complex physical forces. But, studying all this intricate biology leaves me with one final lingering question to consider.
What's that?
When you realize that our lungs are essentially vast, wet, incredibly delicate membranes that require microscopic dish soap and 100-mile-per-hour winds just to stay functional, and they're directly exposed to the outside world 12 times a minute.
Yeah.
What does that mean for human evolution and our long-term health?
That's a huge question.
It is. Our biological shotguns and cilia escalators were brilliantly engineered for the organic dust of the ancient savanna, not the synthetic, microscopic particulates of the modern world. As we continue to spend our lives in environments with increasingly artificial or chemically polluted air, we really have to ask, how long can this miraculous machine keep up?